Recall, kinetic molecular theory states for ideal gases, that is, gases at high temperatures and low pressures, or large volumes, we can essentially ignore the volume of the particles and the interactions or forces between them. For gases like this, we can use the ideal gas law. But what if we increase the pressure by decreasing the volume? Now there is less space for the particles to be in. And at lower temperatures, the particles have less kinetic energy, thus less velocity. They're moving slower. Now we can't ignore the particle volumes and interparticle forces. These are commonly referred to as real gases or non-ideal gases. We'll have to account for these factors when calculating the gas pressure. While a few equations have been proposed, van der Waals equation is most commonly used in general chemistry. Van der Waals equation attempts to find the observed pressure of a real gas. Notice how the equation is built off the ideal gas law, but with two obvious corrections. The minus NB term is called the volume correction, and the minus A N over V squared term is called the pressure correction. Let's discuss these corrections. Since the gas is now restricted to a smaller volume, the volume must be corrected, and this is dependent on the size of the particles. The particles are taking up space too. Next, the force of the collisions are reduced because of the attractive interparticle forces. This includes collisions with the wall of the container, thus less pressure. There needs to be a pressure correction. Let's return to van der Waals equation. A and B are called van der Waals coefficients for the volume and pressure corrections, respectively. Here are some coefficients for a few gases. I've chosen helium, neon, xenon, and water for this exercise. Helium and neon are small noble gases with small polarizabilities, therefore exhibit weak interparticle interactions. Their coefficients are very small compared with xenon and water. Xenon is a very large atom compared to helium and neon, and thus more polarizable. Therefore, xenon atoms interact strongly with each other. Water is a very polar molecule, thus exhibits strong intermolecular interactions. The coefficients for xenon and water are much larger. Let's compare the pressures from the ideal gas equation to van der Waals equation, and I'll start with the ideal gas equation. Let's find the pressure for 1 mole of 1 liter of each gas at 273.15 K. Of course, the ideal gas law will give the same pressure for all the gases, 22.4 atmospheres. This would be the same pressure for all gases if they behaved ideally. Now let's use van der Waals equation to find the pressure for helium first. The equation may look busy, but try to keep the equation organized by completing the calculation in parts. Start by finding the volume correction, then finding the uncorrected pressure, then subtracting the pressure correction. Interesting for helium, the pressure observed from the van der Waals equation is 22.9 atmospheres. Notice the ideal gas law pressure closely resembles the observed pressure. The van der Waals pressure for neon is 22.6 atmospheres. Interestingly, the ideal gas law gives a pressure to within a 2 and 1% error, respectively, for helium and neon. Now, let's look at the observed pressures for xenon and water. You can see the observed pressures from van der Waals equation of 19.4 and 17.6 atmospheres for xenon and water, respectively. These represent a 15 and 27% error, respectively, compared to the ideal gas law pressure. In all honesty, under normal conditions experienced in lab or on Earth, the ideal gas law would work fine. but under special conditions, van der Waals equation might work best.